How does a tree grow? Why does the wind blow? When does a flower bloom? How can a rocket shoot to the stars or land up on the moon? It's science and technology, engineering, mathematics. Get smart, keep it simple. Let's learn about STEM.
Hey friends, we're going to jump into buoyancy today. So what is buoyancy? Buoyancy is an object's tendency to float in a fluid. A fluid is a liquid or a gas. We're going to be using water as our liquid of choice today to show a little bit more about buoyancy so we can understand what makes an object buoyant. Density is a huge factor when talking about whether or not something is buoyant. So whether or not something is going to float or stay up in a fluid. The buoyant force acting on an object is the fluid's tendency to push up against that object. That's the buoyant force. It's an upwards force. It wants to lift an object up. You can think of a boat in water or even a hot air balloon in the air around us. So it does not have to just be water. The fluid can be any kind of liquid or gas. The shape of an object also can have an effect on its buoyancy. Let's get started with some simple shapes like this brick I found in my yard. It smells like dirt. I did kind of rinse it off a little bit. So do we think that it will be buoyant? Is it going to float in the water? I'm going to say no. Definitely not. It went straight to the bottom. It would have dropped a lot faster if I had let it go, but I don't want to bust out the bottom of my tank. So this brick is not buoyant. So what does that tell us about the density of this brick versus the density of the water? The density of this brick is much higher than the water's density. Okay, well, what about this bowl? So this bowl is made of ceramic. And ceramic is more dense than water, but it also has a bowl shape to it. It's not just a ball of ceramic. It's got this hollow space inside that's filled with air. And air is much less dense than water. So do we think that this will be buoyant or not? Let's see. We've also got a lip here that's going to trap some air. So this ring here, this lip on the bottom of that bowl, air is going to get trapped in here if I set it just right. So I think that this will float on the surface of the water. How about that? Okay, but what if these hollow cavities were filled with water? Do we think it would sink or float? If that ceramic is more dense than water, what's it going to do? It sinks. So then what does that tell us about buoyancy and the shape of a vessel? That the shape does affect an object's buoyancy. Well, why is that? Because when a shape can hold air within it, it changes the overall density of what the water is trying to lift up with its buoyant force. The water is no longer just holding up or trying to hold up that ceramic material. You have to account for that air in there. Okay, well, what about some aluminum? Aluminum is a metal, so it is pretty dense. It is more dense than water. So what if I'm going to take a square about this big, I'm going to make another one. They are the same size. One of these I'm going to fold up into a bowl shape and see if I can get it to float. So I have this fantastic bowl-shaped aluminum. I'm going to take this other piece of aluminum, I'm going to wad it up, I'm going to pack the aluminum as tightly as I possibly can. Okay, so what is this going to do? What does this due to the density of these objects. So it's the same amount of aluminum in these shapes, but the aluminum here is packed a lot more tightly. So which one's more dense? This ball. And this is less dense because it's spread out over a larger area. The water is not only pushing against aluminum, it's now pushing up against air, and air is way less dense than water. So I'm gonna take this spoon and really mash this down tight. I want it to be really, really packed. Okay, so we've got the same amount of aluminum again, but it's shaped differently, so the overall shapes will have a different density. I'm gonna put both of these in the water. This one floats because, again, you've got that air inside it and the water has enough buoyant force on this object to keep it afloat. But what about this one? Oh my goodness. It floated too. It didn't want to at first. I must not have all the air out of this. Hold on. I am now stepping on it. Okay, let's try that again. Oh my gosh. Okay, so if anything, this should really help you understand how much less dense air is than water, because just the little amount of air that was still trapped inside that aluminum foil was keeping it afloat. If this still floats, I'm gonna have to get a hammer and smash this together even better. Oh, thank goodness. Okay, so it sank. Oh, about to make me look foolish. So this does sink because I've mashed almost all of the air out of here. I'm sure there's still a little bit more because I was just poking it really hard with a spoon, but that just goes to show how much less dense air is than water and how huge vessels made of heavy materials can float because of the air that's within them. So you think of like a huge cruise ship, that's humongous and made of metals and filled with furniture and slides and pools of water even in the middle of the ocean. And those boats still float in the water because air is so very, 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 very not dense at all. Even crazy shapes like these boats will float. It has air trapped inside. But what happens if I fill those air-filled cavities with water? It goes down and it sinks. There's still a little air trapped up in here and it's trying, but it sinks as well. Shake all that air out of there. And plastic is also not as dense as aluminum foil. So it's wanting to stay afloat a little bit, but obviously not as well as when it was filled with air. Let's see, just for curiosity's sake, I want to know if this toy boat can hold this big brick up. Like we saw with the aluminum foil, air is awfully good at displacing weight and keeping things afloat and making things buoyant. But this brick is pretty heavy, so I'm just, for curiosity's sake, would like to see. Nope, not quite. That boat is not big enough, it's not displacing enough water, it's not filled with enough air to be low enough in density to stay afloat and be buoyant. But it was worth trying out. I would love for y'all to go do this experiment on your own. Try to look all around your home. Try to see what is buoyant and what is not. Try to create your own aluminum foil boat and see how many little rocks you could put inside. You can go around your yard and find some small pebbles, make you a little bowl like this, or you could even try to shape it into a nice little fishing boat shape and get some rocks and count and see how many you can fit inside before it sinks. You could also grab an apple, see if it's buoyant or not, or a lemon. Ooh, a little bit less buoyant than the apple, but it's staying up there. So just grab a few objects from around your house and see what you can come up with. I would love to know how many rocks you can fit in a homemade boat. Thank you so much for tuning in. I hope you learned something about buoyancy. I hope you learned a little bit more about density as well. And we hope you'll join us next time where we get smart, keep it simple, and learn about STEM. Bye! Thank you so much for watching. Here are some other videos you might like. And make sure you subscribe so you can see when new videos are uploaded and we can keep getting smart, keeping it simple, and learning about STEM.